Okay, in this lesson, we're going to be learning how to solve exponential equations. So these are equations with exponential functions in it. We're going to use two methods. One method is by finding a common base, and the other method will be using logarithms. So let's take a look. Method number one. In this case, we have an exponential function. We have two exponents here, actually. And method number one is when they have the same base, it's quite straightforward. All we need to do is set the exponents to be equal to each other. And that kind of makes sense. When the base is the same, if the exponents are the same as well, then we have a true equation. So we can reduce this equation to x is equal to 2x minus 5. That's super straightforward to solve x is equal to 5. But what do we do when the bases aren't the same? In this case, it's kind of a variation on this method. Sometimes it's possible to create or to restructure or rewrite the exponent or the base such that the bases are the same. So in this case, we could take the 4 and turn that into 2 squared. And let's not forget the x here. So we're just basically substituting the 4 into 2 squared, equivalent version. Similarly, I want to take the 1/2 and turn that also into a base with 2 in it. And so that's 2 to the negative 1. And then we have x minus 3 here. So again, all I've done is I've taken the 1/2 and I've translated it, turned it into an equivalent number, but with a base of 2 instead. And so now I'm going to use my exponent properties and multiply my powers here. So I have 2 to the 2x is equal to 2 to the negative x plus 3. And so you can see over here I had this negative 1 and I distributed it here because I'm multiplying negative 1 times this entire quantity x minus 3, so I need to distribute the negative 1 both to the x as well as to the negative 3 here. And so that's why it becomes negative x plus 3. So you can see this distribution right there. So now I have two bases that are the same, and so I could just set the exponents to be equal to each other, and now I have a very simple equation again to solve. Okay. So you can go ahead and try these out. We're going to move on here. Now here's another case. Method number 2 is when actually we cannot make the bases the same. There's no way for us to make the 4 to have the same base as the 11. It's not like the previous example where we had 4 and 1/2 and we were able to make a common base of 2. There's no way we can do this. So in this case, we will use logs. We look at this, and this is 4 to the, has a base of 4, so we're going to use log to the base 4. We're going to apply log to the base 4 to both sides of the equation. We choose log to the base 4 because we see 4 to the x power here. These kind of cancel each other, counteract each other, they undo each other, and so then the left-hand side simply becomes x, and then we have log base 4 of 11. At this point, we could use our calculator to then create or figure out the decimal version for this. Let's look at another example. A little more complicated, but the same idea will play out. In this case, we want to get down to a point where we have the exponent function all by itself, e to the 3x, and then my numbers on the right hand side. So the first thing we're going to do is we're going to deal with the additive term here first. So we're going to subtract 11 from both sides. And still we have this negative 5 term being multiplied here, so we're going to deal with that second. We're going to divide both sides by negative 5. Now we have e to the 3x is equal to 16/5. Now to deal with this exponent function, we're going to take the natural log of both sides. Remember, natural log is this implied base of e. And so now we have these two inverse functions here kind of counteracting each other, undoing each other. And so now the left-hand side becomes simply 3x is equal to the natural log of 16/5. And we can punch that into a calculator. Becomes 1.16. Divide by 3, and we find that x is equal to 0.39. Okay, let's move on to the final applications here. We have this Newton's law of cooling. This equation is used if we want to see how the temperature of an object changes over time. So we could have the initial temperature, T0, stands for the initial temperature of some object. It's sitting in a room, so this is our room temperature, the surrounding room temperature, TR, T sub R. And then we have some cooling rate. So we have an exponential function here with the cooling rate of R here. And over time, the temperature of the object starts to approach the temperature of the room, and the temperature T here can be calculated by plugging in kind of the various values. So let's look at an example. We have a car, and it overheated, and it overheated at 280 degrees. That's our initial temperature. It can be driven again once it hits 230 degrees. If the cooling rate is 0.0048 and the outside room temperature is 80 degrees, how long will it take? So we want to find T here. How long will it take before you can continue driving? So let's kind of break this down. We have our initial temperature of the engine. That's T sub 0. We have the temperature that we would like to achieve so that we can drive the car again. That's T, which is equal to 230 degrees. We have the room temperature, which is 80 degrees. And we have the cooling rate, which is 0.0048. And so what we want to find T. So we plug in all these values into the equation, and we want to then work towards solving for T. So we do some simplification. We get rid of the additive term first, the 80. We subtract 80 from both sides. 230 minus 80 is 150. Now 280 here minus 80 is 200, so now we have to deal with this multiplicative term right here. We're going to divide both sides of the equation by 200. And finally we have the exponential term all by itself. So once we have the exponential term all by itself, we take the natural log of both sides. Natural log is with the base e. And we have these inverse functions here, the natural log and the e to the power of. Those are inverse functions, and so the right-hand side simply becomes negative 0.48t. And now we have a simple equation right here to solve. We plugged natural log 0.75 into a calculator, and it gives us negative 0.2877. We divide by 0.0048, and we get T is equal to 60, so about 60 minutes. So that's how we can apply this whole concept of solving exponential functions using Newton's law of cooling.